All right, the second section of chapter 15 talks about line integrals. Now, before we can talk about line integrals, we need to talk about piecewise smooth curves. R of t, x of ti plus y of tj, t going from a to b, is smooth when this R of t is back to the first chapter. We did paths. The derivative of x in relationship to t and the derivative of y in relationship to t are continuous from a to b, and they're not zero at the same time. If that's the case, then it is piecewise smooth. Notice this curve from 0, 0, 0 to 0, 2, 0 to 1, 2, 0 to 1, 2, 1. Okay, it's smooth. Each piece is smooth. Now, it's jerky, so it's not a smooth curve, but it's piecewise smooth. Curve 1 going from 0, 0, 0 to 0, 0, 2. So the x is going from 0 to 0, so x of t is 0. The y is going from 0 to 2. So it is 2t if we let t go from 0 to 1. And z is going from 0 to 0. So the first curve, piecewise, is 2tj, t going from 0 to 1. Now the second piece, now x is changing from 0 to 1. T is constant, z is still 0, so x is going, because we ended at 1, so now we're starting at 1. So 1 minus 1 is 0. So t minus 1, 2 plus 1, t minus 1 gives me 0 to 1. Y is a constant, z is a constant, so t minus 1i plus 2j, t going from 1 to 2. And then finally, x is going from 1 to 1, so x is a constant. T is going from 2 to 2, t is a constant. Z is going from 0 to 1. It's changing. So now we're starting, we ended at 2, so t now starts at 2. So we are going and looking at the result there, okay, that should be t minus 2. Because if t is 2, 2 minus 2 is 0. If t is 3, so it's 1i, 2j, and t minus 2k, t going from 2 to 3. And that path is piecewise smooth. That path is piecewise smooth. Okay? So the key to parameterization of a curve is the orientation. Okay? So we have to be able to look at the orientation and know how it's going. So we've talked about the integral from a to b of f of x dx. Okay? We've talked about integrals that look like that. We studied those kind of single integrals. We've now studied double integrals over the curve, over the region, f of x, y, dA, integral over the region. And now we're integrating over the curve. And we're integrating over the curve. So what is this line integral? Well, here's the definition. Okay. Integral is a limit of a sum. So that's what it is. The integral of c of f of x, y, ds. ds is arc length. And so in a plane, the limit as the deltas are approaching 0 of the summation of I go from 1 to infinity of the function at xi, yi, delta si. And on 3 dimensions, it looks like that. Now, pretty obvious, we do not want to use that to find our line integral. So we need some way to do it. In fact, the majority of this class, the rest of the way, is going to be formulas that help us do some things. Towards the back of the chapter, you will find this table and summary of line integrals and how to find line integrals, some of surface integrals. We'll talk about those later in the class. The second chart, find towards the back of the book. Okay. Fundamental theorem of calculus, and then the fundamental theorem of line integrals. talk about that a little bit later. Green's theorem and divergence theorem, Stokes theorem, but formulas. Because the basic rule is I can't do a line integral. I've got to be able to work with it and change it. And so the first thing we find is ds, which turns out to be the derivative of the x component squared plus the derivative of the y component squared in 3 dimensions, the derivative of the z component squared, dt. So we are trying to evaluate this line integral over this curve. We have to have a piecewise smooth curve on a closed interval. And so this becomes the integral from a to b of the function, replacing x with x of t and y with y of t, and ds with the square root of the derivative of x squared plus the derivative of y squared dt. And so we're substituting. Same thing as we substitute into there. So line integrals, evaluating line integrals. So if we had this line integral, here's the curve. It's gone from 0, 0, 0 to 1, 2, 1. So we need to figure out the curve. Well, the x is going from 0 to 1, y from 0 to 2, the z from 0 to 1. So we let x be t and y be 2t, and z be t going from 0 to 1, I can then use this definition. Summation of x squared, x is t squared, minus y was 2t, plus 3z, z was t was ranging from 0 to 1. ds, the derivative of of x is 1, square it, of 2t, derivative of it is 2, square it, derivative of t is 1, square it, you get the square root of 6. I now have substituted into there, and I can now evaluate the line integral. That's how we evaluate line integrals. Evaluating line integrals. And so when you are given a line integral to evaluate, you need to think through it and do a substitution. You cannot evaluate a line integral without some kind of formula. Now the application is work. Work, definition, if f is a continuous vector field, r of t is a smooth curve from a to b, the line integral of f onto c, so the line integral of f dot dr on c, this is work. This is the definition of work. Right? So work, again, I can't do that. So what do I have to do? I have to substitute. In place of, if this is a vector field in x, y, and z, I need to have my curve. I need to substitute in place of x of t, y of t, z of t, allow the function to work on it, dot with the derivative of r prime dt from a to b, and that would be how we figure out what the work that is done. Okay? That's how we figure out what work is done. Again, example. Here is our vector field. Minus 1/2 xi, minus 1/2 yj, plus 1/4 k. And here's our path. Okay, so we are looking at going from 1, 0, 0 to minus 1, 0, 3. Okay, we are looking at that path. Here's our path, that helix. And here are vectors. If you go to any point and put this guy, you're going to get those vectors. So that's the picture. So what is this work? Well, it's that integral. So f is, we're going to work on x. Okay, x is going to be the cosine. We're going to work on y. Y is the sine. We're working on z. Z is t. So the function takes minus 1/2 xi, so minus 1/2 cosine of ti, minus 1/2 yj, so minus 1/2 sine tj, 1/4 k, so 1/4, and k in our problem here, right? K is going to be the t value there, so going to be 1/4. Okay? And here's our function, so just 1/4 k. The derivative of this is minus sine of t, I plus cosine of tj plus k. Take the dot product, going from 0 to 3 pi, and we can find the work done. Okay. Line integrals. Line integrals. Okay. Now, line integrals can show up in different ways, in different looks, and yet they're still a line integral. So work when f of xy is mi plus nj, one of the forms we had. We looked at being conservative with these vector fields. So the integral from a to b of m dx plus n dy is another way of writing this vector field. Another way of writing it. So if it's given in this form, here's work. Integral of the curve, there's the curve. Here is m dx plus n dy. And so you do your substitution. And so it's going to be work is m dx, so 3 cosine t plus 3 sine t. So it's going to be y cubed, so 3 cosine, so y cubed, 3 sine t cubed, plus x cubed, 3 cosine t cubed, plus 3 xy squared. So you substitute in those values, dt, going from 0 to 2 pi, because we're going around the circle one time. Right? This is a circle. Our path is a circle affected by this vector field, and we can get the result. And so line integrals. Line integrals. We can't evaluate them directly. We have to make the proper substitutions along the way. And so there's a couple of ways of doing line integrals.